Hello everyone. This video is going to be the start of the proof chapter of the course. I'm going to be giving quite a lot of examples in this video, so what I'd like to do is pause them at your first opportunity, get the notes down in your book or wherever you want to write them, have a go at the examples, and then unpause so that you can see me do the solutions. Okay, so the start of the course is going to be to do with kind of mathematical language and logic. So I've got a starter on the screen already, and I want you to have a look at the sentence I've got in blue, which is that if you attend Harrington, you have to wear a uniform. That is, of course, true. We've got a uniform policy. And then in red, I'd like you to read through them carefully and decide which of them are necessarily also true, given that the statement in the blue box is true. Okay, so as I said, pause the video, have a think, write down which of the red sentences are also true. Okay, hopefully you've had a chance to have a look at that. So let's take a look at them in turn. So for part A, we're saying that if you don't attend Harrington, then you don't have to wear a uniform. Well, that's clearly not true. Just because you're not at Harrington, you could be at some other inferior college that doesn't require you to wear a uniform. Why you'd want to do that, I don't actually know. But nevertheless, the statement isn't true. For part B, if you have to wear a uniform, then you attend Harrington. Well, again, that's not true. Just because you have to wear a uniform, you could be at a college other than Harrington that has a uniform policy. So that's not true either, okay? You don't have to be attending Harrington. For part C, though, if you don't have to wear a uniform, then you don't attend Harrington. Well, that one, in fact, is true. If you were attending Harrington, then you'd have to wear a uniform. So the fact that you don't have to wear the uniform means that you can't be going to Harrington. So this third one is the only one of the three that's true. Okay, now looking at the structure of these sentences, we can describe them using mathematical language. So I'm going to introduce that now. So you'll notice that our initial statement up here in blue is of this form. It's what we call a conditional statement, and it's of the form P implies Q. Okay, P is the first part of the sentence. If you attend Harrington. And that's what we call the hypothesis. And from that hypothesis, we are kind of inferring this conclusion, which is that you have to wear a uniform. So Q is what we call the conclusion. Okay, and then what we're doing with these red statements is we're kind of playing about with the structure of this sentence. Okay, the initial one says P implies Q. So this arrow here being the implication symbol, or it means implies when you read it. So what we're doing with this one is we're saying not attending Harrington. Well, that's not P, isn't it? So we're changing the structure to not P, and then we're saying that it implies not Q. Okay, we don't have to wear a uniform. Okay, so by changing the structure to not P implies not Q, we get what's called the inverse of the statement. Okay, which negates each of the two parts of the sentence, and it maintains the same order. Okay, not P implies not Q. And as we've said, this inverse isn't necessarily true. Okay, doing this to the sentence doesn't make another true statement. For part B, if you have to wear a uniform, that's the second part, that's the conclusion, that's Q. Then you attend Harrington. So that's changed the structure to Q implies P. And that change in order gets what you call the converse of the statement. Okay, and again, the converse of a statement isn't necessarily true either. You can think of maybe different examples where if you change the order of the implication, it doesn't necessarily work. For part C, if we negate in the opposite order, so this is going to be not wearing a uniform, that's not Q, then it is in fact true that that implies not P. Okay, so what we have then is that P implies Q and not Q implies not P are actually logically equivalent. If one is true, then the other is true. And this is what we call the contrapositive. Okay, contra kind of meaning against, and positive is like the forward direction of the argument. So to summarize then, we're happy to have this as being true if the initial is true. So a statement and its contrapositive are logically equivalent. Okay, so basically, if you can show that one of these is true, then the other must be true as well, but not the case for the other two types, okay, for the inverse and the converse. Okay, great. So that's a little introduction to some maths language that you use there in terms of proofs and kind of conditional statements. I'm going to spend a little bit more time talking about this symbol here as the implication symbol. So next up, we've got another symbol for what happens if the statement and its converse are both true. So if P implies Q and also Q implies P, which remember isn't always the case, but in the case that it is true, then we can combine that into this statement here. And this has got a kind of a double-headed arrow that points both ways. So this says P if and only if Q. That's how we read it in kind of formal language. And then that shortens down to P if Q, if having two Fs like that. Okay, so that's quite a strong statement. That normally shows that two statements are equivalent, because if one is true, then the other is true. And if Q is true, then P is true. Okay. Right, let's look at two quick examples, and then for the remaining ones, I want you to kind of fill in the gaps with the appropriate symbol in between. So firstly, we've got n is divisible by 6, if and only if n is divisible by 2 and 3. Okay, so that's perfectly true. If a number is divisible by 6, then you can show that it's divisible by 2 and 3. And then on the other hand, if a number is divisible by 2 and by 3, then that means that it's divisible by 6. So that implication does work both ways. For the second example, I've got a triangle with lengths A, B, and C. I've put the angle theta up here between A and B. And then it's also true that theta is 90 degrees if and only if A squared plus B squared equals C squared. Okay, so again, that's a kind of two-sided implication. If the angle is 90, then Pythagoras will hold. And if Pythagoras holds, and we can show that, then we know that the angle is 90. Okay, so these two things are effectively equivalent. Okay, so now's your chance to read through the rest of my examples. Bearing in mind there's two down the bottom here. There's F over here and G over here. Read through them, pause the video, and then I want you to fill in the gaps with this arrow that points to the right, this arrow that points to the left, or the if and only if symbol that we've just learned. Okay, so take your time, have a read through, and then wait a few seconds for the solutions. Okay, great. Hopefully you had a chance to go through those. So maybe if you can think of some mathematical examples, you'll be able to tell which way around this arrow points. So if n is divisible by 15, and then we've got over here n is divisible by 5. Well, numbers that are divisible by 15, all of them are divisible by 5. But not all numbers in the 5 times table, such as 10 or 25, are divisible by 15. So the implication is going to go this way for this example. Okay, if it's divisible by 15, then it's divisible by 5, but not the other way around. Okay, similarly then for B, today is Easter, that being Easter Sunday, and then we've got tomorrow is Monday. So let's think about this again. So Easter is on a Sunday. If it's Easter, then it's a Sunday, which then means that tomorrow is Monday. So we've at least got it this way round. But if it's Monday, tomorrow, that doesn't mean that it's Easter today. Okay, not all Sundays are Easter Sundays. So again, the arrow points that way. Okay, part C. X is a rational number, and then we've got X has a terminating decimal. So let's maybe draw some examples up for this in this margin here. So if I've got a terminating decimal, let's think of 1.3. That's terminating because the decimal stops, and it's rational as well because it's 13 over 10. Okay, and in fact, if any terminating decimal, you can use powers of 10 as a denominator to make a rational number. So it looks like we've got the arrow this way, pointing left, because terminating decimals are rational. But you can think of rational numbers which aren't terminating. So for example, nice easy one, 0.666 recurring. That is rational. It's 2/3, but it's not terminating. So the arrow only points in that direction. Okay, part D, very similar. X is rational, and then X has a recurring decimal. So if your number is rational, it doesn't necessarily have a recurring decimal, so we can't point out to the right, but a recurring decimal can always be made into a rational number, so again, it's going to point this way. Okay, E. So suppose you've got a triangle T, we've got all the angles are 60 degrees, and then we've got T is equilateral. Well, if all the angles are 60, then the sides will all be equal when you construct it, so it's going to point this way. And then also, if it's an equilateral triangle, all the sides are the same, but then that will mean that the angles are all the same as well, so this is an if and only if case. So double-headed arrow for that one. For F, we've got sine theta is bigger than 0, and then theta is acute. Well, if your angle is acute, then we know from the sine graph, which I should probably draw. So 90 degrees is here. Acute angles live in this first little piece. If it's acute, then yes, sine is going to be positive, so we can point this way. But because this is a periodic graph, if I can continue, we're going to get more angles. Well, in fact, we're going to get more angles in the obtuse case where sine theta is positive as well. So it's only going to point this way, okay? Just because sine theta is positive doesn't mean that the angle is acute, but if the angle is acute, then sine theta will be positive. Okay, finally, my red herring is G. G is a square, and then you've got P has 4 equal sides. Hopefully you didn't fall into my trap, but if you did, it's a good learning point. Squares have indeed 4 equal sides, so we can point this way. But a shape with 4 equal sides may not be a square. You might not have thought of a rhombus. So that rhombus disproves the case that points to the left. Just because it's got 4 equal sides doesn't mean that it's a square, so it only points that way. Okay, hopefully you got those right. We're going to move on now. We're going to look at methods of proof now. Now we've got kind of to grips with the structure of a kind of mathematical sentence and implication. We can kind of talk about how we actually prove these things. Because so far we've only really kind of thought about whether or not they're true without proving them. Okay, so we've looked at a lot of these in year 12, I think, but it's worth us going through the different methods and looking at some really classic examples that are likely to come up in an exam so that you're really kind of fluent with them and you know exactly how to set them out. Okay, so I'm going to kind of go through these in roughly order of increasing difficulty. So starting off with the kind of easiest type of proof. I guess it's not really a type of proof because it's a disproof, but it's disproof by counterexample. So we're using this to show that a statement of the form P implies Q is not true. So to do that, we are going to, well, all we have to do is find a single example where P is true, but then Q is false, okay? And that will disprove that every time P is true, then Q has to be true as well. So it's quite easy to do this. Most of the time, the examiner is going to give you an example that's quite easy to kind of think of a counterexample, hopefully. So again, if you want to read through these before I go through them, pause the video, see if you can work out a disproof. Some of the ones towards the bottom might be a bit more tricky, but I'll leave it to you to take your time and try and think of a disproof yourself. Okay, right, let's try and find some disproofs for these then. So we've got, first of all, n is prime implies that n plus 1 is composite, which I've used to mean not prime. So hopefully you thought of the immediate example, which is that when n is 2, that fails, right? Because 2 is prime, but then 3 is not composite, okay? Doesn't mean that 3 is composite. Okay, well, I suppose I should take this out. I'll say but. I'll reword this actually, that makes more sense to do that. So if 2 is prime, but 3 is also prime. Okay, and in fact, that's the only counterexample we could possibly find, right? Because primes are all odd apart from 2. This is the only time where you get consecutive numbers, both of which are prime. Okay, right, second example, so you've got a and b. This means that they are both integers. And we've also got a squared equals b squared, and we're showing, well, we're assuming that implies that a equals b, but we're going to disprove that. So hopefully you've thought of some examples. So let's take, I guess, a equals 3, b equals minus 3. You've probably thought of something similar to that. So then 3 squared equals minus 3 squared. They're both integers as well. Make sure we're checking all of the conditions we've got. So these are both 9, but 3 is not the same as minus 3. Okay, great. Third example. This one is a little bit more tricky to find the counterexample. Maybe you've done it with a bit of Googling, but we'll see. So we've got n is prime, implies that 2 to the n minus 1 is also prime. You might try some small primes, and you might kind of fail to disprove it for a few moments. But then if you try, I believe, 11, that's the first occasion where it fails. So if you do 2 to the, well, clearly 11 is prime, but 2 to the 11 minus 1 is 2047. But that's 23 times 89, which means it's got factors other than 1 on itself, which means it's not a prime. Okay. Right, fourth example. A and B are irrational numbers, okay, not fractions. And then that implies that A plus B is irrational. Okay, so on the face of it, this looks like it should probably be true, right? A and B being irrational means they're kind of nasty decimals. And you might think that if you add nasty decimals together, you're going to get another nasty decimal. But not the case, okay? We can disprove that. It's quite a sneaky example, but it's one I've seen in a previous exam paper, so it's worth paying attention to this one. So here's my kind of sneaky proof. So if you take A to be pi, okay, pi is famously irrational. And then you take B to be something like 1 minus pi. Okay, then we've satisfied the hypothesis. Both of these are irrational, but their sum is pi plus 1 minus pi, which makes 1, is not irrational. Okay, it's a rational number, clearly, because it's 1. It's 1 over 1. And I'm going to write it like this. It belongs to the quotients. Okay, so we've disproved it. Okay, quite, yeah, as I say, quite sneaky, but it's one that now you know how to do it. It's kind of, you can add it to your repertoire. All right, finally, another one that kind of might take a while to find the counterexample, but you've got n is a positive integer. Implies that n is the sum of 3 squares. Okay, and by squares, I'm also including 0 in that because 0 squared makes a square number as well. Right, so hopefully you've played about with some numbers. Let's have a look through. So positive integers means we're starting at 1. So if n is 1, then that's going to be 0 squared plus 0 squared plus 1 squared. Ah, damn. Okay, fine. We've failed that one. N is 2, right, what's 2? That's going to be 0 squared plus 1 squared plus 1 squared. Okay, that one still works. N is 3. What's that going to be? That's going to be... I don't... Oh, no, 1 squared plus 1 squared plus 1 squared. There we go. Almost fell for that one. Okay, N is 4. I reckon I can do that one. That's going to be 0 squared plus 0 squared plus 2 squared. N is 5, I can do that one as well. That's 0 squared and 1 squared and 2 squared. N is 6, I can do that as well. That's going to be 1 squared plus 1 squared plus 2 squared. And then N is 7, I think is the first time where that's going to fail. I don't think N is 7 is possible, so we're going to kind of give up there. Okay, try it for yourself. Try and find 3 squares that make 7. You can't do it. Okay, perfect. All right, so hopefully you get the idea of that. You just have to find one place where it fails, and we've disproved the entire statement like that. Okay, to finish off the video, I'm going to do one more method of proof, and then in a separate video, I'll go through some more types that you're probably familiar with as well. And the first main type of proof that we're going to look at is called direct proof. Okay, again, I think it's something that I probably showed you last year, but it's worth having another go. So, we're now proving a true statement now. So we're not, rather than disproving, we're proving that P implies Q. And it works by basically setting out a kind of rigorous mathematical argument through some logical steps. So the first thing we're going to do is assume that P is true. And then to show this implication directly, we're going to unpack some definitions. So what does it mean for P to be true? If it talks about odd numbers or even numbers, we can unpack that and write some maths down. And then you go through some logical steps, you do some maths, some kind of mathsy magic, and then you finally show that Q is true at the end. So it should be a kind of logical chain of events through some maths towards the answer. Okay, right, I've got 3 examples to finish off the video. If you want to try them yourself, you can do that before I show you, and then that will be it for today, and we'll leave it for the rest of the week to finish that off. Okay, so we're going to prove using this method that if n is the product of 3 consecutive numbers, then n is divisible by 6. Okay, so just as a bit of advice, when I'm thinking of divisibility, if I see a composite number like 6, I'm probably tempted to split that into its prime factors, because showing that a prime divides a number is typically easier than showing that a composite number will divide a number. So I'm going to split that into 2 times 3 just to kind of think about how I might approach this proof. So we saw in a previous slide, if we can show that 2 and 3 divide this number, then we've shown that 6 divides the number as well. Okay, so let's firstly unpack the definition of this 3 consecutive number business, and then we'll do this thing with 2 and 3. Right, so here's my proof. So n is my number. It's the product of 3 consecutive numbers. So I'm going to write 3 consecutive numbers down times together. That's going to be a times a plus 1 times a plus 2. Okay, so that's the unpacking bit done. Right, now I've got to think about these 3 numbers times together and think about where this 2 and 3 is going to come in. Now, seeing as they're all in a row, it's not too difficult to kind of think about where that's going to come in. If I've got 3 consecutive numbers, then clearly one of them has to be even, right? If you think about rows of 3 numbers in a row, then no matter how you do it, you're always going to get an even number. Okay, in this case, the even's in the middle. If I do 28, 29, 30, then the end ones are even. Okay, so no matter how you do it, clearly you're going to get an even one. So we're going to talk about these factors. One of them must be even, and by one I mean at least one. Okay, and then in the same way, if there's 3 in a row, then what you've got to have is that one of them is a multiple of 3. Yeah, because there's no other possibility. In our examples, this one divides by 3. In our example here, the 30 divides by 3. So as well, 1 must be a multiple of 3. Okay, so together we're pretty much done because we've shown that it divides by 2 because that's what it means to be even. I'm just going to put div because that's what I am. And then here n is div by 3. So together that means that n is divisible by 6 and we're done. Okay, so a little bit of thought going into these factors, but if you know what it means to divide by 6, you can probably kind of work out some logical steps there. Okay, this second one is probably the most important example that I'm going to go through because this is an exam favourite for A-level. All right, I've seen it in several different exam past papers, so it's really worth you knowing this one off by heart. A-level favourite, there we go. And I'm going to do a bunch of exclamation marks just to really highlight that point there. Okay, so prove that. If x and y are positive real numbers, then x plus y over 2 is greater than or equal to the square root of x times y. Okay, now it's worth knowing that when you read through a statement like this, every single word counts. Okay, mathematicians are notoriously pedantic about the language they use. So positive here is going to be just as important as everything else. All right, so you've got positive real numbers as well, and then these 2 things we're trying to show. All right, it's worth kind of pointing out that these 2 expressions are quite famous. So this, you'll notice, is the mean, but it's specifically the arithmetic mean, which is kind of the usual mean that you kind of first learn when you're in secondary school. And this one, it's also a type of mean, but it's not the arithmetic mean, it's called the geometric mean. It's like the timesy mean, the multiplication mean, if you like. Okay, other mean brands are available. So we're going to prove this using all the information that we've got. So I'm going to start my proof by writing this out again. I'm going to do some logical steps. Okay, and because I've got an inequality to deal with, I've got to be really careful that I'm not doing anything illegal that's going to break the direction of this inequality. Okay, I might be tempted to do something that might change the direction of this. I want to avoid myself doing that. However, the first thing I'm going to do is times by 2. That's perfectly fine. That's kosher. I can times by 2. 2 is positive, so it won't change the order of things. Okay, right, here's where the fun starts. So I'm going to now look at this square root and realise that it's probably something I want to get rid of. So I'm now going to square both sides. Okay, right, this is where the positive aspects of the problem comes in. I'm not allowed to square both sides of an inequality unless I'm sure that both sides are positive. So I'm going to write that down. Okay, so x plus y, if I've got positive numbers here, their sum is clearly positive, and then a product as well is also positive, so the right side is positive too. So I can do that. And also, it's not usual or typically allowed to put negatives inside of square roots. So that's another reason why we're having these positive numbers. Okay, so let's square both sides. X plus y squared greater than or equal to, and then 2 will square to make 4, and then this root will square to just make xy. Okay, doesn't that look much nicer? So we're now going to expand out the brackets. That's probably the next step you probably thought of, and then we're going to tidy up, and it's going to make something really nice. So x plus y all squared. Let's not make the rookie error. X squared first. 2 times the product in the middle, don't forget. Plus y squared. Bigger than or equal to 4xy. Okay, great. So that's expanded out. I'm now going to spot I've got like terms with the xy's. I'm going to subtract 4xy to the left side. That's going to make it into minus 2xy plus y squared bigger than or equal to 0. And then what's nice about this left side is that it nicely factorizes itself. It's actually this. It's x minus y times x minus y is bigger than or equal to 0. And then, of course, this is the same bracket twice, so it's x minus y all squared. Okay, so that's the kind of logical chain of reasoning here that gets you to this. A mark scheme, a lot of the time, is going to run through this backwards. Okay, an examiner is normally expecting you to start with this and then end up back at the beginning again. But I think it's kind of it's more logical to start on this side, because then this doesn't kind of come out of nowhere, if you like. So now we're here. We can finish this off. We've got a square bracket. A square is always going to be non-negative because it's something that's been squared. So we can conclude that this is always going to be true. Okay, but we are restricting to positive real numbers, so it's always true for positive xy. Okay, if it's true for any numbers, then it's certainly going to be true when they're positive. So we're done. And when we're finished with a proof, we put a little box just to finish it off, because why not? Okay, great. That's our famous one done. Okay, please learn that one off by heart. Okay, I can't stress enough how many times it comes up. Right, finally, we're on the home straight now. I've got one more example. It's a little bit of a number theory problem. Okay, we're involving integers here. Again, have a go. It's a little bit more tricky than others that you've seen in this video, but hopefully, I believe in you. I think you can have a go and get quite far with it. Unpack the definitions, see what you can do. Pause the video, and then I'll go through it in a second. Okay, right, let's give this one a shot, shall we? So let's read through carefully. We've got A and B, they're non-zero integers. The non-zero part is probably important, okay? It's not just there for decoration. A divides B, in other words, A is a factor of B, and B divides A. So we've got both of these. Then we're showing that A must be plus or minus B. So that's pretty obvious if you think about some examples. If you've got two numbers that divide each other, then the only way that can happen is if they're either the same or if one is the negative of the other, right? You can think of some examples there, but we're going to prove it's always going to work. So let's start by unpacking the definitions. So we've got A divides B. What does that mean? Well, it means that there's some number I can multiply A by to get to B. So let's write that as an equation. So A M equals B. And of course, for this kind of definition to work, m is an integer. Okay, that's going to be a little bit important later. Right, that's great. Equations I can work with, words not so much. B divides A, I can do something similar. So again, I can multiply B by something to get to A. So that means that B times N equals A. I don't know yet how M and N are related to each other, but we're going to do some showing in a second. And again, N is an integer. Okay, right, let's see what we can do with these two equations, right? I want to hopefully show something about M and N. So if I've got B here, I can probably stick it in that B, and then that's going to maybe do some cancelling out. So let's sub one into the other. So I'm going to maybe number the equations. So here's 1, here's 2. I'm going to sub 1 into 2. I'm going to put the B's where the B's go. So now I've got this. I've got, right, AM, which is B, times N equals A, right? And then what I'm going to do is I'm going to divide both sides by A, okay? It won't be A, will it be 1? Okay, divide by A, divide by A. Why am I allowed to do that? Well, I'm allowed to do that because these are non-zero integers, A and B. If A happened to be negative, this wouldn't work because I can't divide by 0. But because it's non-zero, I can do this. All right, so Mn equals 1. M and N are integers. So what does that mean? Well, this means that these numbers divide into 1. And what integers divide into 1? So the only way that can happen, the only integers that divide into 1 are 1 and minus 1. Okay, so let's think about what could happen there. So let's suppose, well, I only really need to look at the first equation here to finish this off. If I think about this equation, so case 1, if m is 1, because that's one possibility, then that just means that A equals B because m becomes 1. And if m happens to be minus 1, that's case 2. Then looking at equation 1 again, m is minus 1, that means that minus A equals B, or in other words, A equals minus B. Right, so we are done because we've shown that no matter what's happening here, this means that A and B are either the same or negative, so we're actually finished. All right, congratulations, you've reached the end of this video. Hopefully you've had a good lesson and that you've taken something away from these examples, that your maths has improved, and I hope you have a great day. I'll see you soon and enjoy your weekend.